We would like to ask if you could please refrain from video, audio, or photo recording of all talks. Many of our speakers have kindly agreed to share their slides with you, and these are available within the literature section on the platform. Please remember that we encourage debate and discussion and welcome all of you to use our networking services to introduce yourselves to other attendees. But we do not permit the overt solicitation of products or services and reserve the right to block any user who infringes on this rule. It's also incredibly important to say that this event was only made possible thanks to the generosity of our sponsors and partners, particularly our Platinum sponsor Agilent and our Technology Spotlight sponsors Eppendorf Americas, LabVantage, PAL System and Agilent. For more detailed instructions on how to make the most of the features available to you at this event, please navigate to the event home and watch the overview video at the top of the page, or visit the FAQ section in the left-hand menu. With that out of the way, I'm now very pleased to introduce our opening panel session. So in this panel session, I'm delighted to be joined by three members of the Food Authenticity Network who will be discussing how to use and interpret untargeted testing for food authenticity. This is a fully live session, so please feel free to send in your questions throughout, and we'll address as many as we can during the second half of the session. Without further ado, I'll hand over to our leading panellist, John, to introduce himself.
Thank you, Heather, and thank you to Technology Networks for the opportunity to be here today. So we're pleased to be able to kick off this event where we've got a session on the sort of untargeted test methods often used in food authenticity analysis. And what we're going to do is have a roundtable discussion, the three of us, for about half an hour. And then we're going to open it up for questions. So please put your questions in the sidebar on the app here. But first off, we'd better introduce ourselves, I suppose. So I'll start with myself. I'm John Points. I'm based here in the UK. So good afternoon to everybody, rather than good morning. And I advise food companies on managing risks in their ingredient supply, and particularly on the use of analytical testing and how that best fits within their overall supply assurance strategy. But one of the many hats I have is I'm secretary of something called the Food Authenticity Network. And that's the reason I'm here today. And for those of you who haven't heard of the Food Authenticity Network, I would really urge you to Google it and sign up. It's free, and it is a great repository of resources, both for food authenticity analytical testing and for food fraud mitigation. So we've got a lot of signposting on there to resources, to best practice, to methods and things like that. But one key area for us is to connect food industry with testing laboratories and getting them both to understand each other's language. And to that end, I'm really delighted to be joined by two real experts on the topic today from our Centres of Expertise laboratories. So first, to the left on my screen, certainly, I've got Kate Kemsley.
Hello everyone, yes, I'm Kate Kemsley. I'm a Professor of AI and Chemistry at the University of East Anglia. We're in Norwich in the east of England. My scientific specialism is computational statistics, and for most of my career I've been interested in how these methods can be applied to the data produced by instrumental techniques of analytical chemistry. That's things like infrared, NMR, mass spec, and that's frequently in the context of food authenticity applications.
Thank you, Kate. And to my right on my screen, I've got Catherine Frankis.
Thanks, John. Hi, everybody. My name is Catherine Frankis. I'm a chemistry technical specialist at a company called Reading Scientific Services Ltd, based here in the UK. I use various chemical analysis techniques to provide solutions to analytical problems within the food industry. And these can be wide-ranging, but do often include questions around food authenticity and adulteration analysis specifically. Within my technical experience, I've had a broad exposure to different types of chromatography and spectroscopy techniques, and so consider myself fairly well versed in what does and doesn't work for particular applications.
No, thank you, and thank you both. So yes, as I say, we're we're going to have a session on untargeted test methods. So probably better start off by explaining what untargeted testing means, really. I don't know, could I pitch that one to you, Kate?
Yes, sure. So to me, untargeted analysis refers to a broad brush approach to analytical testing. So you may have the goal of detecting and identifying as many compounds as possible in a sample without prior knowledge of what specific compounds will be useful to you, which ones you're looking for. And I'd make the contrast with targeted analysis, where we have a focus on measuring a specific known compound. So, for example, in a direct targeted approach, we might measure the concentration of a specific pesticide residue in a food sample, and we might then compare that to a predefined limit for safe consumption. And in an indirect targeted method, we might look at, say, a nitrogen isotope ratio in crops and use that to determine whether we're dealing with organic or mineral fertilizers. And that's not by measuring the fertilizer itself, but by using a marker that's causally connected to the type of agricultural practice. But true untargeted analysis would involve collecting multidimensional measurements without any specific compounds in mind initially. So, for instance, we might use techniques like mass spectrometry or infrared or NMR spectroscopy to generate profiles which contain information on many different compounds present in the sample. There'll still be some selection by compound class, but a very broad brush approach. And then we can apply statistical methods to the data set as a whole and identify patterns or anomalies against that profile. So for authenticity applications, that will commonly involve collecting data from a large reference database and comparing any incoming profiles to those.
Okay. No, thanks for that. That's fairly clear, I think. But given that, I mean, I suppose the obvious question is why would you use untargeted analysis rather than look for a particular marker like a nitrogen isotope if you knew there was a cause and effect between somebody conducting a fraud and a particular marker? Why would you go for untargeted analysis rather than targeted? Kathy, let you come in.
Yeah, okay, thanks, John. So traditional methods of targeted analysis to show authenticity will be looking for maybe one or two markers, and that's an analytical, very straightforward method of working. But once those markers have been identified and well understood, it is possible that those wishing to misrepresent products or undertake food fraud, it is possible for them to take that information and to maybe fake a positive response using additives or some kind of masking. And that allows a way into the food fraud approach. So what non-targeted analysis allows us to do is, rather than generating one or two markers that can then be manipulated, it looks more at a wider population of variables and markers, and gives a more generalistic representation of what good looks like. An example where targeted analysis has maybe fallen down in the past would be the melamine milk scandal in Asia, where toxic melamine was added to milk powders in order to generate an artificially high nitrogen result, where in that case nitrogen was being assessed as the target compound for high protein. And so here we have a really good example of where fraudsters have used a targeted analytical approach and have found a way around that. So a non-targeted method would hopefully prevent that kind of fraud from happening.
So in principle, could you apply it to anything? I mean, Kate spoke about patterns. Could you find a pattern for anything?
So when you're looking at an appropriate analytical technique to use for a particular non-targeted analysis strategy, it is important that there is scientific rationale for the differences that you are trying to track between populations. So, for example, Kate mentioned isotopic ratio, and this is quite oftenly the key way of distinguishing between products from different geographical origins, or maybe if we're looking at lipid profile differences in meats, something like an LC-MS approach might be better, because that is a technique that's more amenable for profiling those types of molecules. Sugar profiles and organic acids are crucial for fruit juices and honey authenticity. So spectroscopic profiling, potentially by high resolution NMR, might be best used here, because a profile can give information that is particularly good for non-volatile small molecules. Or alternatively, if there is a need to look at volatiles, maybe due to flavor profiling being the key area of interest, then a technique such as GCMS might be more appropriate. And in all cases, it's really important to look at what's been done before. So a thorough literature search would be needed to see which techniques have shown promise previously in the field, and what the analytical drivers would be for the differences in the populations that you are trying to track. And it may well be that that maybe the analytical capabilities that you have locally are not absolutely appropriate for what you're trying to show. And although it's tempting to set up models in the piece of kit that is in the room next door, it may well be that you need to look wider within your network to understand where you can get the analytical data collected. But generally, with non-targeted analysis, this type of source data sometimes is not actually as critical as what you do with the data after you have it. There are different pre-processing requirements that would be specific for different types of data acquisition strategies, but really it's how you interpret that data and how you model it that gives you the meaningful output.
Okay, so it's not, although it is based on correlation, it's not purely correlation. Ideally, you want some sort of scientific causation of why the things you're measuring might be varying. Yeah. Now, I quite like that idea. The risks of basically having a good technique and a really good application and a good model, and then searching around for things to use it on, rather than the other way around. Why should I use this technique for this problem? But yeah. So as we said, I mean, it's predicated on building patterns and pictures of what authentic looks like with the data you collect. So I don't know, Kate, do you want to expand a little bit more about that? Because that's quite a critical aspect of it, isn't it? How you build that?
Absolutely. I would say so. So I come from a slightly different perspective. We're not really analytical testers as our primary motivation for doing this. It's much more about researching novel methods and suitable methods for tackling challenging authenticity problems. And for us, in an authenticity study, it's securing that supply of authentic samples as the first step, which is absolutely critical. I mean, if they're going to be the reference collection which you're going to use as the basis of all your modelling, they absolutely, beyond doubt, need to be reliable in terms of their identity. So at times that's meant collecting them ourselves, or literally growing things ourselves, or only using very trusted agents, or working, for instance, with research organisations in other producer countries. But absolutely getting the reference collection right and containing only totally authentic samples of known provenance, identity, whatever, is absolutely critical. And another point that's worth remembering is that for these multivariate statistical methods and database handling methods, we need large numbers of samples, and that's especially if we're going to use untargeted multivariate stats on them. So it's important to consider all the sources of variation might contribute to a large database and cover all those bases. So what I mean by that is if we're looking at some sort of natural product that has seasonal variability or agricultural processing variability, we need to cover all of those. So for a full working method, that might mean collecting samples for 2, 3, 4 years and building all of those into your reference database before you can be pretty certain that that's going to work going forward into the future. The alternative to that is to go a bit early, but be very, very clear, for instance, in communicating to a customer that the method scope is really defined by the sample types and the sample variability in your reference collection.
Yeah, no, absolutely. So if you want to offer a testing services for organic oranges that are Spanish and verify they're Spanish and organic, you've got to collect Spanish organic oranges from every type of conditions that might be grown in Spain, every type of season. You can't just go down the supermarket and buy organic oranges labelled as Spanish and build your laboratory references.
No, exactly. I mean, you have to collect routinely from different places over a period of time. That also models your experimental variability and your machine variability over a period of time, and operator variability. All the things that go together to make up the variance that underlies the data set need to be captured as best as you can.
Yeah. So I don't know, Kathy, have you come across that when building database? I mean, how easy is that in practice?
Yeah, so I mean, a point to mention there, I think, is what Kate talked about, seasonality, and making sure that all variability that comes with your natural product are taken into account in the database that you generate. But also, these databases are often not able to stay static. You will find that as well as natural variability season to season, that generally the relative levels of analytes can change over time. So you need to look at your database and you need to estimate what the lifespan is of that database. And maybe samples need to be dropped out of the database in a few years' time. And you're consistently making sure that your database is topped up with new samples and the old ones are dropped out.
Yeah, no, absolutely. So assuming you do, I mean, this is the hard bit, isn't it? The hard bit is collecting the samples.
That's the expensive bit, yeah.
But assuming you do manage to that, then what sort of things, how do you actually build these databases, build these models, Kathy?
Sure, yeah. So, I mean, I suppose the type of data that you collect will be dependent on the techniques that you have decided to use, or that is best for the question you're trying to answer. But as Kate mentioned as well there, you need to ensure that your data sets are fully representative of the population that you intend to test against. And there is lots of discussion about what a minimum number of samples should be that makes up your database. But that's, as Kate said, in an ideal world, we would have lots and lots of samples, but sometimes that's not possible. And so you do have to be realistic in terms of what you can achieve. But in terms of the actual data acquisition, the type of data that you're going to be acquiring, that is very dependent on the techniques that you're going to be using. So, for example, Kate and myself do a lot of NMR analysis. So generally, we would be collecting a one-dimensional NMR spectrum. Normally, we apply a water suppression experiment because generally we're looking at aqueous populations, but we don't want our water to interfere with our data collection. But there is the additional possibility of collecting more complex data sets, especially at high resolution spectrometers, where although you might not use them routinely in building a database, if you do acquire, or you do happen upon a sample that doesn't fit in your database or gives a non-conforming result, you can actually look at that data and try and further interpret what it is that has driven that test sample to not be compliant. So you've almost got that extra data there in case you need it. In a majority of cases, I did mention earlier, data would need to be pre-processed as well, and the degree of pre-processing or what pre-processing needs to be undertaken will be depending on the analysis that you do.
So what do you mean by pre-processing? Sorry.
Yeah, sure. So for NMR, for example, we need to calibrate on our chemical shift scale. It's essentially the measure by which all our molecules are affected by a magnetic field. So we include an internal standard into our extractions, and then we calibrate that to make sure that all our peaks, all our signals, I should say, line up. And something very similar would need to be applied to a chromatography-based approach. There are various ways of peak aligning chromatograms to make sure that all your peaks line up, irrespective of column usage or or any other effects that would change your retention time slightly.
Okay, got it. So some kind of standardization of the data.
Absolutely. And then once all your data is standardized, there may be further pre-processing that you need to apply. So in NIR, for example, you're often looking at the derivative curves rather than the Fourier transform curves to see the subtleties in population differences. Or in NMR, when we're using high resolution, we often use approaches like binning or bucketing. So rather than looking at hundreds of thousands of data points across our full spectrum, we'd then be looking at a reduced number, and potentially also using tools like statistical ranking to understand which of those data points are most significant in driving differences between our sample populations.
Okay. So you've done that. You've got your 200 authentic Spanish organic oranges or whatever. You've told your system that's what they are. You've measured, I don't know, you've got 1,000 mass spectral points for each one, or God knows how many hundreds NMR peaks you get for each one. So you've got all that standardized data. What's this term chemometrics? I mean, what does the black box do with it? Well, that's probably a hard one for you, Kate.
Whatever you want it to, John. I shouldn't say that. So chemometrics is a very broad term for all kinds of analytical techniques or statistical techniques for analysing chemical data. That's all it really means. But what I will talk about a little bit is one of the most well-known ones, which is used far, far wider than just within chemical data, and that's principal component analysis, which I'm guessing you've heard of. I would say that once you've got your matrix of data, so as Kathy said, the first step is pre-processing, registration, normalization, scaling, all those things that go on, and they vary by technique, but they're really, really important, and actually they can end up being more important for your outcomes than the choice of modeling method you use, in truth. But I'm assuming you've got a square matrix of all your cleaned data. I'd say the first step that I would always do is visualizing that in a different perspective, just to look for anything interesting or unusual in a very straightforward way. And actually, principal component analysis is very straightforward and it's very effective. So it works by transforming each multidimensional measurement, so that's each row in your data matrix, into a much smaller set of numbers, usually only a few, maybe 4 or 5 important ones. And then you can plot those very small data sets as single points on pairs of principal component axes. So you're going from a situation where you've got 200 peak area collections from mass spectrometry. So maybe, I don't know, 200 samples and 100 peak areas, to then only having 200 samples and maybe 3 principal components. And you can plot those 3 against one another, even on a 3D coordinate system, or maybe just 2D, 2 at a time. And that may well show you patterns, clusters, outliers. It's a simplification process that can make these things much easier to spot than trying to look at a large matrix on its own to start with. Once you've done that, that doesn't actually make any assumptions about the data. It's just viewing it from a different perspective. There's no modelling as such going on in that at all. But then what we normally want to do is some supervised modelling, and that will be effectively drawing some rings around a class or a group that you're interested in. So in the case of authentic Spanish oranges, you want to put a ring of some sort around that grouping. And then test whether anything new that you analyse falls within that boundary or not. So that's called supervised modelling, where we start with our known class or classes, and you can do it as one class or multiple class modelling. And I think keeping it simple is always a good idea. One straightforward way to do this is by placing a confidence interval or a boundary around that class using a method like SIMCA. So that draws a ring in PC space. That's a very well-known method. It's very effective. But actually, there are many other ways to arrive at a set of supervised classification rules and many software packages to choose from, which can all be quite daunting. But actually, there'll always be some minor differences between them, but the results they give should be broadly the same. You shouldn't really be in a situation, it would be a bit odd if one approach fails completely, whereas another one or others are very successful. And in that case, I might do something like revisit some of the assumptions you're making about the data at the point of normalization or scaling, or whether you're doing something implicitly different due to the way that the model's been implemented in the software package. So a good tip would be to be really up on what some of these front-ended software packages are actually doing to your data set. So yeah, that's really what I've got to say about it. Could go on forever about chemometry.
I've got to admit, I come from an analytical background, and I sort of get worried sometimes. I basically don't understand what the black boxes are doing, and I think it's quite important that you do. I mean, one of the key things, as I understand it, is the validation, particularly if you're using some of these modeling and machine learning, that you reserve a set of data that the model's never seen before. Is that correct? So
yes, that's
and then
exactly
you can use
right.
that to validate your classification.
Yes, and I would say that there's no substitute for doing that. You should always have a holdout set of completely independent test samples. You might want them to be compatible with your reference data set, but it's not a good idea to have them in any way being even vaguely biological replicates or technical replicates, certainly not, but not even, I don't know, fruit picked from the same orchard. It'd be better for them to be fruit picked from the same orchard the following year, or from a different orchard, and no crossover between orchards, for instance. Yeah, the reason you want to do this validation is not just it's good practice to make sure that sort of that you're not actually inadvertently not using independent samples. It's also to guard against a numerical overfitting. So overfitting is where you've overcomplicated your model and incorporated not just information about the underlying makeup of the samples, is sort of important chemical information, but you've inadvertently added in noise. And some multivariate modelling methods are worse than others at this, and they can incorporate so much noise without you fully being aware that you'll end up getting a really, really good outcome, even by internal cross-validation on your training set, but it won't work as well on new incoming data. And that's really because you've made your model overcomplicated by adding in more and more principal component dimensions, for example. You can always tell whether that's happened by bringing in your holdout set of completely unseen data. And really, if you've got no overfitting happening at all, then you'll get pretty much the same success rate in classification on that holdout data. Usually you won't, because it's almost impossible to guard against all overfitting, but you will pick up howling obvious problems of a big difference between success rates for the training and the test sets.
Yeah, I mean, I try and think of things in pictures, in clusters of results, but you can't really do that in 5 dimensions, can you? You think of overfitting as a model to tell the difference between fingers and air, and you draw your line like that.
Yes.
Where actually you should draw it like
yes,
that.
You're right. You can't. The nearest equivalent would be that you would never collect one data point and then expect to put a straight line fit through it. You can't do it. But that's the situation that we're in the multivariate space very often, that we've got maybe 200 samples, but we've collected 1,000 mass spec peaks or 10,000 NMR data points. We've got far more numbers per measurement than we've got discrete samples in our reference database. So we're always in the position where we've got one point on a graph and we want to estimate a line, a calibration line through it. We can't do it. We need these tricks like principal component regression or other types of methods which kind of get a way around it, but they're not absolutely foolproof, and you can misuse them. And the only way to test that you haven't overcooked your model is by bringing in some independent test data. At least it can never hurt. Don't ever not do it. There's no reason not to.
Yeah, I mean, Kathy, I know you're from more of a service laboratory background, and actually trying to provide these analytical services and build these models. So how does somebody from an analytical background and upbringing go about effectively appreciating all these nuances and understanding the black box?
Yeah, I mean, it's a challenge, but I think what we should say is that the vast range of analytical techniques that are currently being harnessed in this field and the incredible advances in machine learning mean that authenticity screeners are sort of being sold alongside quite a lot of software packages, and we should celebrate that, because it means that things are being, it's more accessible to people to start building models and start understanding what's going on with their samples. But the downside is exactly what you said, the black box solutions. And we as scientists need to never accept a pass-fail result just because the software tells us that. We need to really understand what the model is that's being utilized, and the ability, if we want to take that data out of that software and run it in an independent statistical software. We use Jump or Minitab or other software, I'm sure is available, in order to rationalize these findings ourselves and not trust a yes/no answer that comes from an add-on into a piece of software where we don't know exactly what the workings of the algorithms that are working there. But also, I always think it's important that once a feature has been selected, and this is something that you can do with NMR quite nicely, you want to make sure that the scientific rationale for that feature being identified makes sense. So can you align it or correlate it to a particular chemical entity that you can then rationalize as being elevated in particular populations, for example? Is there scientific rationale for the model that you have happened upon and that you have validated? And I think that's really important as scientists, because we're matching up the statistics and the maths with the chemistry and what's actually happening.
Yeah, that's what it's a really silly example, but I've always thought in principle you could find pattern correlation differences between anything, couldn't you? In principle, a food could have a claim on it, harvested by moonlight, and you test one set harvested by moonlight and one set harvested by daylight, and you see a difference between them. The very fact gives that difference. In principle, could give you the justification for building a test design on that, but common sense tells you no.
Yeah, isn't there a saying that you can prove anything with statistics except the truth? I saw that quote online recently. I think the point is that if you are looking for a specific correlation within a wide range of data variables, you will invariably find it, which is why the cross-validation exercises are really important. And those cross-validation exercises are done so many times, and so you really have the truth and the belief in what your model's telling you. Kate, I'm sure you've got some comments on that as well.
I have. As I said, there are methods, and neural networks is one of them, which can find a solution which will classify your data set according to any kind of random classification labels that you care to provide, if you don't cross-validate. If you use validation, internal validation, that won't happen. Without it, it will, because it's numerically possible to do that. And that's because there are far more parameters than you've got samples. It's fairly simple. Cross-validation helps. It's not a total panacea, because again, you're only, depending on how you do the splitting, you are still to a degree not really you're still using all of the data as both training and test samples. So it's not exactly the same as leaving a holdout set and just coming back to it at the end. I keep banging on about that, but it is honestly the best way to be certain that your methods work. And there's not a lot that people can say about what you've done if you've got a test reference database that you haven't used at all in modelling. And that doesn't mean swapping things in and out until things work best. It means literally leaving it to one side and seeing how your model works. on your sort of mad example of whether, common sense says you can't tell harvested by moonlight, but there are some other ideas as well which are worth bringing in, which is that you need to be aware when you're planning experiments, you don't inadvertently introduce data artifacts from the way you make the measurements, which end up producing a classification difference. So an example would be running all the samples from your class 1, your authentic set or your moonlight set in the first week, and then coming back after the weekend, servicing the machine, cleaning the machine, and then running all of your class 2 or non-authentic samples. If you then find, somewhat surprisingly, that you can actually tell the difference between the two data collections, two data classes, you couldn't really be 100% certain that that wasn't due to some subtle effect of your instrument changing. So that sort of thing you've got to be bear in mind, and that there's actually really no substitute for always randomizing your sample collections when you run them. Again, it's good practice to run blanks from time to time so that you can look at things like machine drift. The thing about these things is that they don't hurt and they may benefit you. So I would say that type of planning is good practice. And again, it's worth reiterating that technical or biological replicates are absolutely not independent test samples and shouldn't ever be considered as such. So those sorts of things I would say are worth bearing in mind. They feel kind of quite basic, but they don't always get done. So worth bearing that in mind.
Yeah, I mean, I know, having sat on both sides of the fence, and I'll finish it off because I know we promised some questions. I've sat from the laboratory side and also from the industry side, from the customer side, and from an industry side, we've got no appreciation of any of this. You see a laboratory that's offering, we've got a database to tell if your apples are organic or conventional, and you send them a sample and they get a result back, and it says this sample is not consistent with being organic. So okay, it's not then. You don't see, all of this stuff is back end for them basically, and that's a little bit scary for me sometimes. But anyway, sorry, I'll go off on a rant. But we should allow some questions to come in, Heather, because I know that there's been a few submitted, haven't there? I can see them popping along the side of the screen there.
Lovely. Thank you so much, John, Kate and Kathy. That was really interesting. So yes, we have had lots of questions come in. So we've had questions come through from the live session, but also we've had questions pre-submitted when people registered. So thank you so much if you are in here viewing, if you sent in a pre-registration question, but please do continue to send them in and we will grab as many as we can. So something that I thought was quite interesting that was asked, considering that obviously all three of you have very different specialisms and you work within industry in different areas, but you are all part of the Food Authenticity Network. And someone has asked what the aims and objectives of the Food Authenticity Network are and how you operate.
I'm more than happy to take that one quickly. I say if you're not familiar with it, then have a Google. But basically, it's a global online platform. Effectively, it's an online platform designed to help point people towards best practice in both mitigating the risk of food fraud and in analytical test methods and the best use of analytical test methods. It's grown a lot over 10 years. It was effectively set up in the UK by the UK government after the horse meat in beef scandal. And their thought was in the first instance, they just wanted a network of laboratories which could respond to future incidents. But it soon became clear that it was much, the need was much greater than that. So at the moment, we've got, 5,000 odd members. They're signed up, they get a monthly email summary of issues and publications. So we've got a website that points towards different best practice and resources. We go through scientific publications and produce little digests. We have a network of expert laboratories, and different laboratories have got different specialisms. Some are expert in testing some kinds of food, some are expert in testing some kind of technique. So it's funded. It's basically crowded funded by partners. So if you're interested in funding as well, we'd be very interested in it. But it's a free to join open access platform. So yes, go and have a look, please.
Wonderful. Thank you so much for that answer. And I guess a quick follow-up on that one is, are there any set criteria that one has to meet to be part of the Food Authenticity Network?
Not really. We've got a variety of stakeholders as members. We've got regulators, we've got people from analytical backgrounds, we've got industry professionals, we've got consultants, students, journalists. Basically, as long as you're not an AI bot, we'll have you.
Perfect. Good news for everyone here, I think, then. Marvellous. So I'll move on to some of the more technical questions that we've had in. So I know that throughout we've discussed a few different methodologies that you use for testing. And this may end up being a question for you, Kathy, as I know you're the most active with analysis at the moment. We spoke about lots of mass spec, but do you consider imaging to be an important tool for demonstrating food quality? And is there an opportunity for non-visible, such as X-ray inspection?
Yeah, I think that's a great question, actually. And sometimes we underuse or under consider imaging as a tool within this area. But it can be incredibly useful, especially when it's coupled with modern image analysis approaches. So again, it's harnessing modern computing strategies and power, really, so that a computer can look at hundreds of thousands of images and based on automatic thresholds and various other criteria, it can select what kind of shapes it wants to be looking at or it needs to be looking at, and it can conduct calculations on those shapes incredibly quickly. So just for an example, I mean, I can imagine a situation where the authenticity of a particular seed might be shown using its morphology, and in olden days gone by, people would have to actually look at these things under the microscope. But with a high-speed camera coupled with image analysis that could be calculating aspect ratio or sphericity, then that could be used as a measure of authenticity. Non-visible imaging, I think, is a really interesting one. I suppose something like X-ray tomography is an incredibly useful technique to look inside something. So whether that's to do with the microstructure, again, of a seed, of a natural product, of a fruit or a vegetable, or I suppose if we're thinking about finished product, manufacturer's product, in the confectionery industry, for example, or in wafers or biscuits, that kind of thing, understanding the internal texture and the internal structure. And that might be critical in a fraudulent product case, showing that a fraudulent product is in fact not genuine, could be as subtle as how the internal microstructure of a material appears. And of course, if you can do that without having to cut open a sample, then that's all the more valuable. So yeah, I think there's definitely potential in those techniques in this area.
Yeah, I mean, there are a number of systems out there, commercial systems out there, and I think particularly for, as you said, seeds and grains, online systems. And I guess if you're a manufacturing handling a particular type of grain or seed with a quite a tight specification, it's quite easy to train a model that just looks at it as it goes past and say, is this different? And that's. But there's even, I saw one now recently about somebody had done a one under a microscope for honey pollen, looking at honey pollen. In the floral class of honey using the AI image recognition technology that's used more likely for picking people out of crowds going into football matches. So it's the pace of change is incredible, isn't it?
I would say the one disadvantage of some of the high-end microscopy techniques is you're looking at such a tiny amount of food, so you're subsampling a macro sample, jars of honey or vats of honey or whatever, and looking at tiny amounts of it. So that's a negative for me. I mean, the holy grail would be being able to run almost everything food-wise past near infrared. on a production line. Wouldn't that be brilliant? So that you were actually, sampling a lot of the food, not some tiny amount. But then, of course, the flip side of that is you haven't got the sensitivity and the specificity.
So you've got to have a very standardized input. So I know that they do it for some grains and seeds. They do it for some milk, dairy inputs in regions of the world where they want to check basically that the milk is not been diluted or authentic or whatever, and they've got NIR on the line there.
I mean, I've seen them like looking at. This isn't authenticity, but this is in production, looking at biscuits over, to check how well they've cooked, whether they're within spec quality-wise. For food quality, it's great, but I think it's always there's a question on the list as well about authenticating food with FTNIR. I think that's the problem. It's great for some things, but not for everything. It's what Kathy said right at the start. You can't go with a technique looking to answer all questions. It's kind of, you need to always match up the strengths and weaknesses of each with what you're trying to do.
Yeah. Do you want to move on to another question, Heather?
Yeah, wonderful. Thank you so much for that. And fabulous, Kate, picking up that other question there. They did sort of kind of go hand in hand. So I think it just highlights the importance of having so many different techniques for different applications and why you need to use a variety. And I'm sure that comes into why these sort of technological tools that are coming more to the forefront now are so important for collating that data across different samples. So another question that I've got that's sort of on the technical line as well, is there a universal sample preparation strategy across the different food matrices for untargeted analysis and food authenticity?
I guess I'll start that one. I think sadly not, unfortunately. I think similarly to there's not one technique fits all, I don't think there's one sample preparation strategy fits all. And again, it does depend on the nature of the matrix, but also the chosen analytical technique and the objective of the testing. So, for example, a lot of analytical techniques will require a solution to either be injected or analysed, and so consideration would need to be taken into how you want to extract your sample in order to achieve a solution that's suitable for analysis. Do you want the fat-based molecules or the water-soluble molecules? And that's obviously going to decide which extraction media you need. Are you going to have interferences by macromolecules? Are you interested in the macromolecules? Do you have to do any cleanup? And if you do clean up, you want to make sure you don't remove anything in your cleanup that's going to be significant in generating your population differences. And then if you don't have to do extractions, if you're lucky enough to have a technique where a solid sample can be assessed, so something like NIR and FTR are ideal for that, as Kate mentioned, because they can be scanned in passing or even using a handheld instrument. So something like seeds or vegetables or something like that. Thinking about, is there a seed is there a shell or a husk that is going to get in? Basically, all the NIR or the detection technique is going to see is the husk. But then when that natural product is potentially processed for use in food production, if that husk is then removed and actually it's the inside of the entity that's useful, then that doesn't help you model what you're trying to model. So yeah, it's unfortunately there's definitely not a one size fits all.
Yeah. I think that pretty much sums it up.
As a very clear and highly covered answer there. Thank you so much. So we've got one really fantastic live question as well, which is actually from Robert Thomas, who is kindly joining us to do a talk tomorrow live. So it's one of our other speakers, so do make sure to catch that as well. So he has asked, can you correlate the trace elemental composition of a soil with the trace elemental composition of a fruit or vegetable and make an assessment about where it was grown?
Yeah, so I mean, I'll have a go at that one. As we've sort of mentioned earlier, isotopic ratios does tend to be the gold standard approach in geographic origin for basically exactly the reason that Robert's mentioned there. And it's to do with naturally occurring isotopes of, say, carbon, oxygen, the proton deuterium ratios, and they can give very specific fingerprints about where in the world these things are grown. And then you also have, as it moves up the food chain, so then the grass is then eaten by the cattle that are being raised. So it gets more complicated as you go up the food chain, but essentially that is a correct assumption.
Yeah, but there's also there are companies that are using trace element profiles as well and coupling it with the stable isotope ratio. So taking all that data, the inorganic and the isotopic ratio, and building models based on that. But I think it comes back to this authentic data collection point, because unfortunately geography doesn't follow national boundaries for one thing. So if you wanted to tell the difference between something that comes from Italy versus something that comes from Slovenia, wine, it's virtually impossible. If you want to tell the difference between something from Europe and South America, it's easier. But if you are wanting to get to that granularity of differentiating quite local geographies of, premium produced food or wine or whatever it might be, you've got to have a really, really detailed data set of authentic samples from that region. And your model is only applicable to that region. So if you want to start looking at another region, you've got to build another model for the other region. So I went to a really good UK AI event yesterday, actually, and one of the guys there came out with a quote that you've got to be watch with machine learning and these models and that the solution isn't more expensive than the problem, and always bear in mind a sense of proportionality. You conceptually, you almost need a database with everything in the planet on it if you're going to try and answer every question. So I don't know. That's my take.
Wonderful. Thank you so much for that answer. So I'm aware that we have about 8 minutes left, so we'll see if we can squeeze in a couple more. So one that I thought was quite interesting is, what do you anticipate as being the greatest challenge in food analysis and authentication in the future?
Everybody take a step back on that one. I don't know. I mean, I suppose that the more claims are made on food, and that seems to be the way things are going, the more authentication challenges there are. So as well as whether something's organic or not organic, or whether it comes from this country or that country, sooner or later you're going to get things like carbon footprints, environmental kite marks, water usage, all sorts of claims on a food that attract a price premium that people want to get to pay for. And it's a question of what's the best way of verifying that. Is it purely digital traceability systems and blockchain and all that sort of thing, or is it analysis, or is it a mix of both? So yeah, unfortunately, the more demand from customers there are for premium products, and the more they're prepared to pay price differentials, the more issues it raises. I can't see the next big thing coming, unfortunately, or I'll make a fortune.
I do think there are some pressures now arising on certain commodities which were not there in the past, but as a result of the changing climate, we know already that Arabica coffee, for instance, is under pressure. It's always been harder to grow than Robusta. There are two main coffee species that are grown commercially, and Arabica is more in demand, but it's harder to grow. And as growers are now finding, they're getting poorer and poorer harvests, and more frequently having production problems, supply problems. And I think whenever you get pressures like that, that's when authenticity issues arise. So I think as we see changing patterns of where things are grown, what's being grown, harvest failures, harvest of certain products failing and others being successful, you'll see more substitution. So that would be I'd see some of the challenges, but we can to a degree anticipate them because we know, what commodities are being produced in good quantities and which are not. So.
Wonderful. Thank you so much. And I think with that mention of the climate impact, I think that follows on nicely to another question that I got that I thought was really interesting from that sort of social aspect. Someone asked, do you think that a rise in poverty worldwide has increased food adulteration activity? And does this impact the techniques being applied?
I mean, I would actually think that the questions are very similar in terms of the comments that John and Kate has made. Is that the globe is under a lot of pressure at the moment, both financial and ecologically as well. And I think those are the pressures that leads to potential opportunities for fraud, food fraud. I think in terms of analytical techniques that may be applicable, we will probably be in a situation where maybe models will be being built in a lab. Maybe we'll get a handle on the variety or the variability of products. But then the important step is going to be miniaturization of that work and of that those modeling capabilities. And so if we can get that right, and if the technology follows, then authenticity could be, or flags to apparent non-authenticity could be something that can be done when shipments are being unloaded, or things are being packaged up. And so really the speed and the technology going into the hands of people on the ground, I think, is going to be quite important as we try and combat these issues.
Yeah, I mean, I don't think it's poverty per se or price differentials, although there's obviously a correlation between regions of the world where there's a lot of poverty and also poor regulation and not the resources for enforcement and oversight and all the rest of it. But I think as Kate alluded to, it's more supply shortages and things, companies not being able to get things, whether it's sunflower oil after the Ukraine war or whatever it may be. But I mean, one thing I always say to people when they're thinking about analysis and risks and all the rest of it is talk to your buyers, because if they know what looks dodgy, if somebody's offering to supply something that they can't get anywhere else for love nor money, then well, how or why? So it's not so much for poverty or the price. I think it's a lot more of a drivers is going to be supply shortages and volatility in supply of food ingredients, and that over a long term that is linked to things like climate change, undoubtedly.
Wonderful. Thank you so much. I think it's really interesting, actually, Kathy, that you brought up miniaturization there. So if the attendee that sent that question in wants more information on that, we do actually have a talk specifically on miniaturization of food analysis, which is opening up tomorrow with Marta Prado from the Iberian National Nanotech. So that would be really interesting to view that and sort of have an idea of that portability sort of on the ground, as you were saying, taking that analysis outside of the laboratory. But I think we'll have to wrap up there, unfortunately. That has gone very quickly. It's been a wonderful hour. Thank you so much for your detailed answers and for such an insightful discussion. So any questions that we didn't get a chance to get to, I know that there are several still waiting in there, but I will forward those across to our three panelists after the session with your details after the event. And as with all of our talks in this event, the discussion will now be available to view whenever you want for the next 30 days within the platform. And that just leaves me to say thank you so much again, John, Kate and Kathy, for joining me, and we'll be back very soon with the next talk for you.
Thank you.